Welcome to a video that introduces the trigonometric functions in terms of right triangles. If you need to build a ramp that has an incline of 6 degrees and must reach a height of 2 feet, how long would the ramp have to be? Well, we can solve this type of problem using trigonometry. There are 6 trigonometric functions, and they are sine, cosine, tangent, cosecant, secant, and cotangent. Customarily, they are abbreviated using this notation in bold. Now, these trig functions can be defined in terms of particular ratios of sides of right triangles. Here are the sine, cosine, and tangent functions in terms of ratios of sides of right triangles. If we start at angle A, it would be the ratio of the opposite side over the hypotenuse. So let's back up here for a second and identify. Remember that the hypotenuse is always opposite the right angle. So if you were to bisect the right angle, the side that you run into would always be the hypotenuse. Now the opposite and adjacent sides will change based upon which angle you're referring to. So going back to angle A, if we bisect angle A, the side that we run into would be the opposite side. So in terms of angle A, this is the opposite side. So the sine of A is the ratio of the opposite over the hypotenuse side. So in this case, it would be A over C. Let's stick with angle A for a moment. The cosine of angle A would be the ratio of the adjacent side over the hypotenuse. Well, if this is the opposite side from angle A, this would be the adjacent side, because this is always the hypotenuse. So the cosine of A would be the ratio of the adjacent side over the hypotenuse, or B over C. And tangent of angle A would be the ratio of the opposite side over the adjacent side. So here we'd have A over B. Okay, now if we look at the second row, notice I'll refer to angle B. So that's going to change the orientation of the opposite and adjacent sides. So if we're referring to angle B, if we were to bisect this, now angle B would be the opposite side, and angle A would be the adjacent side. So notice how regardless of what angle we refer to, the ratio is always the same. Sine is the ratio of the opposite over the hypotenuse, cosine is adjacent over hypotenuse, and tangent is always opposite over adjacent. So looking at angle B now, we have opposite over hypotenuse would be B over C for the sine B. Cosine B would be adjacent over hypotenuse, or A over C. And then tangent of B would be opposite over adjacent, or B over A. One way to remember all of these would be to just remember this acronym, SOHCAHTOA, which stands for the sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Now, before we learned that all right triangles with the same acute angles are similar, and so if we have that case, the trigonometric functions will produce the same ratios because we know that these triangles are proportional. So again, if you take a look at the large right triangle and the small green triangle, they share a common angle here, and they also have two right angles. So based upon angle, these are similar right triangles. So let's go ahead and label this full length. If that's 5 and that's 5, this would be 10. And if this is 4 and this is 4, this would be 8. So for the sine A, we would have the opposite length 6 over the hypotenuse length 10, 6/10. Now if we look at the small triangle, opposite over hypotenuse would be 3/5. And we can see here that 6/10 is equivalent to 3/5, producing the same ratio. The same for the cosine of angle A in the large triangle. We would have 8/10. And in the small triangle, we would have 4/5, which again are equivalent ratios. And for the tangent of A, we would have the opposite over the adjacent, or 6/8 for the large right triangle, and the small would be 3/4, again equivalent. Now let's go ahead and define the three other trigonometric functions, and those are cosecant, secant, and cotangent. And what I want you to notice here is these are reciprocals of the sine, cosine, and tangent functions. So cosecant A would be the ratio of the hypotenuse to the opposite side. Remember that sine was opposite over hypotenuse. And the secant of A would be hypotenuse over adjacent, which is reciprocal of adjacent over hypotenuse, which is cosine. And cotangent is adjacent over opposite, while tangent is opposite over adjacent. So again, all these refer to angle A here. So this would be our hypotenuse. A would be the opposite, and B would be the adjacent. So we can see here, for cosecant A, we have the hypotenuse over the opposite, or C over A. Secant would be hypotenuse over adjacent, C over B. And cotangent would be adjacent over opposite, or B over A.
Pythagorean theorem states that in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides, which are called the legs. So the hypotenuse is the longest side of a right triangle. It's also opposite the right angle, and it must be labeled side C. The reason that's so important is notice that C is on one side of the equation by itself. The two legs are labeled A and B. It doesn't matter which leg is A and which leg is B, because notice they're on the same side of the equal sign. So let's go ahead and call this side A and this side B. So the length of this side squared must equal the length of this side squared plus the length of this side squared. We want to find the length of the missing side of the right triangle. So we'll start with our theorem. C squared equals A squared plus B squared. C must be the hypotenuse, which is this side here because it's opposite the right angle. And these two would be the legs, so we'll label these A and B. Let's go ahead and substitute these values into the theorem, and then we can solve for C. So we'd have C squared equals A squared, or 12 squared, plus B squared, or 9 squared. So we have C squared equals 12 squared is 144. 9 squared is equal to 81. So we have C squared equals 225. And now to find C, we can take the square root of both sides. Now we're only going to take the principal square root, or the positive square root here, because we know C would be a length, and this length can't be negative. 225 is a perfect square, so we have C equals 15, in this case, meters. That's the length of the missing side. Let's go ahead and try another one. If you look at our diagram, now we're trying to find the length of one of the legs. So again, we start with the Pythagorean theorem. This would be side C opposite the right angle. Let's go ahead and call this side A and this side B. So using our Pythagorean theorem, we would have 22 squared must equal A squared, which we don't know, plus 17 squared. 22 squared would be 484, must equal A squared, plus 17 squared equals 289. So now we have to isolate the A squared, so we'll subtract 289 from both sides. So that gives us 195 equals A squared. And we'll square root both sides of the equation. Again, we're only going to find the principal square root. Now, 195 is not a perfect square, so let's go to our calculator. So second x squared brings up the square root, 195. That's approximately 13.96, in this case, centimeters. So we found the length of the missing leg.
Let's determine the sine, cosine, and tangent of angle A. So here's our angle A. Let's go ahead and identify the three sides. Again, this is the hypotenuse. If this is angle A and we bisect it, this would be the opposite side, and this leaves this side as the adjacent side. So again, if we want to, we can use the acronym SOHCAHTOA, if that's helpful. Now before we find these three values, I notice that the length of the hypotenuse is missing. So we're going to have to apply the Pythagorean theorem to find this length. Remember, C squared equals A squared plus B squared. where c is the hypotenuse. So we would have c squared equals 5 squared plus 12 squared. This would be 25 plus 144. C squared equals 169. So C equals 13. You may have recognized this as a 5, 12, 13 right triangle. So the sine of angle A would be the opposite over the hypotenuse, so 12 thirteenths. The cosine of angle A, again, is the adjacent over hypotenuse, so that would be 5 thirteenths. And tangent of A would be opposite over adjacent, or 12 fifths. And that's it. We found those trigonometric values. Let's try one more. Again, I can see right away we're missing the length of this third side. So going back to our Pythagorean theorem, this is our hypotenuse. So we'd have 8 squared equals 4 squared plus x squared. So if we subtract 16 on both sides, we'd have 48. Square root both sides. We only want the principal square root, so we have x equals the square root of 48, but remember 48 is 16 times 3, and the square root of 16 will be 4, so that's equal to 4 square root 3. Okay, let's go ahead and set this up. Now they are asking for cosecant, secant, and cotangent of angle B. So here's the angle we're referring to. So the 4 would be the opposite, and 4 square root 3 would be the adjacent side. Now we can still use the acronym SOHCAHTOA to help us, as long as you know which functions these are the reciprocals of. Cosecant is the reciprocal of the sine function. So if sine is opposite over hypotenuse, cosecant would be hypotenuse over opposite. Well, starting at angle B, the hypotenuse is 8, and the opposite is 4. So we'd have 8 fourths, which equals 2. Secant is the reciprocal of cosine. So if cosine is adjacent over hypotenuse, we want the hypotenuse over the adjacent, which would be 8 over 4 square root 3. Now this simplifies to 2 over square root 3. You may be required to rationalize this. This would rationalize to 2 square root 3 over 3. And lastly, cotangent is the reciprocal of tangent, so we would want the adjacent over the opposite, which would give us 4 square root 3 over 4, which just simplifies to square root 3.